Hi again. So we're going to keep going with our example and talk about the line of best fit. So it says on the scatter plot for drug use, use a ruler or straight edge to draw a line that best models this relationship. Okay, we were saying it's fairly linear. So let me bring this page back up. And I just happen to have a clear little ruler, which is kind of nice because then you can see the data points right through it. So does that look like it would fit? No. And I don't want it to make it too steep either, right? So I want to just going to eyeball it, and we might look for like roughly half the points to be above and half the points to be below. So I don't know, maybe this goes down. I don't know. I'm just going to kind of make a guess. I'm going to draw a line in. So you're welcome to draw yours wherever you like. Okay. And now I'll be bringing this back, I'm sure. Let's see what our next direction says. Okay. So the next thing is draw the vertical distance between each point and the line. Okay. So this vertical distance is a special quantity. It's called the residual. So between each point and the line. So I'll show you what I mean here. And I'll actually take my ruler since I've got it, and I'll do it. So if I were to draw, try to make this as vertical as I can. I'll use the screen to help me. Okay. So if I draw this vertical distance, each point has one, right? Unless it's right on the line. That's the difference between the predicted value and the actual value, right? The line is the model. That's our predicted value. And these are real tiny residuals right there. Okay, so this distance is called a residual. And it's y minus y hat. So I'll show you how we're going to subtract. We can find the value by subtracting. In this class, we're going to be just looking more at whether they're positive or negative. Okay, so if a residual is positive, that means the point, the actual data value, is above the line. So this would be a positive residual, and this would be a negative residual. Okay, so it's a nice way to define it. That way, just anything that's visually, any points above the line have a positive residual, anything below the line has a negative residual. Okay, let me explain that on this sheet. I've got that written out for you. Okay, so the residual is the observed value minus the predicted value. And so the observed value is the y from the original data. Okay, so I'll put y from data. That's the observed data. And then the predicted value we'll see down below. We're going to call that y hat. So this is from the model. Okay, y minus y hat. So if I put that on my diagram here, let me take another one. This is y, and then the point that's right on the line is y hat. So if I go y minus y hat, that's the residual. And so that will be positive if it's above the line and negative if the point is below the line. Okay, so a positive residual means the data point is above the line. So in that case, we say the model underestimates the value for that case. We always talk about the model relative to the data because the model is the one where the error is. Okay, so we talk about the model underestimating because the model is where the error is. The data is what it is, right? It's not low or high, it just is what it is. And then a negative residual, so that was positive residual. A negative residual means the data point is below the line, so the model overestimates the value for that case. Okay, We'll practice with some examples in a little bit, but let's keep going with our line, right? We made this line, and what does this have to do with residuals? So the regression line is another word for the line of best fit, is regression. You may have heard that before or even done it before. And the full name of the method is called the least squares regression line. And it's least squares because it minimizes the sum of the squared residuals. Okay, so think about these residuals as like deviations, because we've calculated standard deviation, right? Where first we take the difference and we square it. But so, well, it's kind of the same thing, right? You're taking the difference and squaring it. And then somebody figured out a formula to minimize the sum of all these squares. Okay, so that's why it's called least squares residual. So it is like trying to get the least deviation overall between the points and the line, right? So that's called the best fit line. Okay, so it minimizes, so that's the least part, the sum of the squared residuals. So that's the squares part, okay? So there are formulas to do this, but we're not going to do it using the formulas. We're going to let technology calculate this for us, okay? So I'm using Staplet, and I think it's a really great app to use. If you have something else you'd rather use, it's fine with me, as long as you're able to show a screenshot of your work. If you're used to using a spreadsheet or something else, you're welcome to use another tool. Maybe try Staplet and see what you think. So here's the formula for our line, and you might be familiar with y equals mx plus b from algebra. It's the formula for a line, same as algebra. The only difference is we use the hat. So we put y hat to indicate that this is coming from data. Okay, so y hat is just like we've done a lot with p hat. This is y hat is how you pronounce that. Okay, so definitely put your hats on. One thing I like about Staplet is it actually puts the hat on the y. A lot of computer systems don't do that, so I think it's really nice that it does that. Okay, so recall the equation of a line from algebra. Since this is from algebra, I didn't put the hat on it. Same thing, y equals mx plus b. And you might remember that m represents the slope. I believe it's French for mountain is why it's m. And then b represents the y-intercept. Okay. A little bit more explanation about this. Y hat is read y hat, and it represents the predicted value of y. Okay, so the predicted response variable. The values of m and b are the parameters. So those are like the inputs of the linear model, m and b. You might also, so some programs use different letters than m and b. So you might see it written as b1 and b0. In that case, it would look like this. Y hat equals b1x plus b0. So that's another way you might see it in a different form. Okay, let me switch to my next page, and I'll be right back. Okay, so on the next page here, it has us going back to Staplet to click on Calculate Least Squares Regression Line. So I'm going to go back over here. So here's where we were on Staplet. We have our scatter plot. We clicked on regression correlation. We got our R. And now I'm going to click on Calculate Least Squares Regression Line. Okay, it gives us a bunch of stuff, but I'm going to scroll back up for the moment and just focus on the scatter plot. So the scatter plot now has a line on it, okay? And it did say, I'm going to go back, it did say linear, right? It does have an option of doing other models below, but it is doing linear first. So we always want to double check, like, does this look like a linear pattern? And then, of course, once we put the line on here, we still need to check, does it still look like a linear pattern? It does look pretty good to me. So I have this for you in our notes, and let's see, this formula's got to be down here below. Yeah, so they put theirs in a box, and it says y hat equals negative 3.0677992. So they're giving us quite a few decimal places. We'll stick with 4, plus 0.61503x. Okay, so it's giving us the full line there. N is the number of data points. So it's always good to double check that the N is correct. So that means you got all the data in there that you wanted. And we're not going to use S or R squared in this class. But again, if you want to know more, take another stats class. We can do inference with statistics as well. Like you can do hypothesis testing around a correlation. You can do it or a slope. You can do it on any parameter. So take Math 244. Or Stat 244. Okay, so let's go back to the notes where I have the regression line right here for you. And I also printed this results box on the notes too. So we have our equation, and then if I was going to write this out on a quiz or an assignment, I would write it with fewer decimal places. I would write negative 3.06, let's see, 0.678. Negative 3, I'm not used to having something before. We've been doing so many probabilities. I'm not used to having a number in front of the decimal. Plus 0.6150, okay? X. We do need the variable in there. Now these could be written in either order, right? So the mx plus b has the x term coming first and then the intercept. So if you wrote it a different way, y hat equals 0.615x, in that case we would put minus 3.0678. Okay, so you could write it either way. The terms are interchangeable as long as you keep the sign in front of it with that term. Okay, so if b is negative, you might also see it written with a minus sign. Okay, a lot of programs don't have the ability to change the plus or minus sign in between, but they will make the value, they'll tell you that either the m or the b is negative, and then that is the same as having a minus sign or subtraction sign. Okay, so let's finish up our example with this data set. Do these results confirm that the increase in marijuana use leads to an increase in other drugs? Okay, so what do you think about that? We've described the association. It's positive, it's strong, it's linear. There's a grouping here, but not anything else very unusual, no outliers. So there's a strong correlation. Does that mean that using marijuana is causing teens to use other drugs? Not necessarily, right? Remember, correlation does not mean causation. So can you think of some other factors that might be involved with both? First thing is there's no time here, so we don't know if any of these teens used marijuana and then the other drug, or the other drug and then marijuana. We don't even know the order in which things happened, right? So first I'm going to say no, because no correlation does not imply causation. Now, if we had some kind of experiment where we had a control group and we had separated out, divided up by random assignment, all the other variables, that's a time we can conclude causation, when there's a randomized controlled experiment. So if we had a graph regarding that, then maybe we could conclude causation, but not just any two data sets, any two variables without controlling for all the other variables. Because what else could influence this, right? These are all different countries. So different countries, let me just write the question. What else could influence? Influence both marijuana and other drug use. Okay, so maybe you can think of some things. Some things I'm thinking about are different policies in a country, right? How do they treat drug use? So different culture and policies in the countries. I mean, even though they're different countries, though, there does seem to be a pattern. What about, as far as individuals, what about trauma? I think there's a big relationship between trauma and looking for coping mechanisms such as drug use. So trauma, maybe socio-economic level. I don't know if that's related or not. It actually may not be. So any variable that you can think of that may be influencing this instead, right? We want to be on the lookout for those. Okay, so list anything else that you can think of. And what these are called is lurking, hidden, and confounding variables. Okay, so we always want to be on the lookout for those. Now, I've separated these into two groups. Lurking and hidden, to me, mean the same thing. And I was doing some research on this because you see different things in different textbooks, and so different authors think about it differently. To me and to a lot of people I was looking online, lurking and hidden kind of mean the same thing. So think of if you're lurking online, you're watching, you're monitoring a discussion or whatever, but you're hidden, you're not participating. So lurking and hidden kind of have the same or very similar meaning. So what that means in statistics is another variable that's actually responsible for the association. So it's a hidden variable that's actually causing both. So it's another variable that's actually responsible, okay? So an example of this would be, got an example right here. Nations with more TV sets have higher life expectancies, okay? Does that mean having a TV makes you live longer? No. In fact, TV could be harmful to your health. But it's the wealth of a nation has more to do with how many, people having TVs and life expectancy because of healthcare and all that. So it's causing a common response. Okay, so this is a lurking or hidden, because it's actually a different variable that's causing the relationship, okay? It's causing a common response. It's causing both the TV sets, more TV sets, and higher life expectancy, okay? Now, to me, confounding is different than that. And sometimes you hear these all used the same interchangeably, but I'm gonna explain it this way. A confounding variable, that has a different meaning to me. That's like a variable is tangled up with the explanatory variable, but it also affects the response variable. So you can't tease out or separate out which variable is responsible for that. Okay, so confounding variable is tangled up with the explanatory variable, and it also affects the response. Okay, so you can't separate it out. So here's an example. Let me put brackets around this example. Okay, for example, when studying the relationship between alcohol consumption and heart disease, whether a person smokes or not is related to alcohol consumption, and it can also affect heart disease. So if you're trying to, make a graph between alcohol consumption and heart disease, smoking, you can't separate that out because maybe someone who drinks more is likely to smoke more, okay, or the other way around as well. So it's related to alcohol consumption and can also affect heart disease, okay? So there are ways to handle this, of course, but that goes beyond the scope of our class, okay? Okay, great. Well, thanks for watching this, and I'll see you in the next video.